If you have been watching this channel, you may recall the video that detailed using a black pill and a generic Bluetooth keyboard to send Morse code. That project, published about 1.5 years ago, was actually a stepping stone to assemble the tool set needed to use an F411 black pill as the heart of an SWR-CW transceiver. Nevertheless, at the time, I felt it showed that for a modest cost and using off-the-shelf parts, it was easily reproducible, and as such was a worthwhile standalone project. But a lot has changed since then, so today I want to revisit the concept and show you how I do it now. The engineer in me is always looking for the minimum needed to accomplish a task. Minimum, as a unit of measure, can vary from situation to situation. 3 common yardsticks are labor, time, and dollars. But when we think in terms of unit costs, dollars, more often than not, is the deciding factor. Chips and electronics in general has seen a lot of inflation over the past 18 months. For example, the USB host board used when the project was originally released was $7.50. Today, from the same source, it's $14. Another project vulnerability is the Bluetooth dongle. At the time, I had 3, and every one was different when it came to negotiating a connection. This bothered me because I didn't know what other variants might be out there. A few weeks back, I found myself at a workshop where the ESP32 was the core building block for some Arduino-like projects. While I knew it had Wi-Fi and Bluetooth built in, it wasn't until getting ready for the workshop I discovered it could act as a Bluetooth host. And its expressive IDF includes libraries to support it. Today, the ESP32 WROOM board is available in the US for approximately $10, while the F411 black pill is now $15. So, porting the project to the ESP cuts the parts cost by almost $20. Additionally, because the Bluetooth is integrated directly into the ESP32, construction is simplified. And finally, the expressive libraries proved to be substantially more robust than the Arduino host libraries I used with the black pill. This means that this iteration of the project is able to negotiate connecting and reconnecting across a larger variety of pairing schemes. However, I still favor Logitech's K380 keyboard as the keyboard of choice for this project. Once connected, the 2 versions are essentially functionally the same. For example, both PCB versions use the same MOSFET to key the transmitter and the same HDYZ electronic buzzer for the onboard side tone. Differences are the ESP32 is configured with a 15-line display, while the black pill was configured with 411 lines. The ESP32 has 2 additional 80-character stored memories, and lastly, on the ESP32, if a key is held down, the character is repeated, whereas the black pill requires a key press for each character entered. In my opinion, in a RAGCHU QSO, these differences are trivial. That being understood, I'm not going to spend a lot of time going over the points that the 2 versions have in common. Instead, ask that you see the earlier video to get an overview of the basics. But really, it's pretty simple. Type in what you want to send and Morse code comes out. Just don't get more than 4 lines ahead of what's currently being sent. Doing so will overrun its ring buffer. Now, let's talk a bit about how to actually replicate the project. To start, this project can be found at this GitHub repository. So go there and review its README file. It should have the key points you'll want. Now, assuming that you've gathered the needed parts, the choice you'll be faced with is to work with the source code or use the repository's bin file and directly flash your ESP. Again, the README file has the links needed to take the second option. And to be honest, direct flashing is about as easy as it gets. So if programming isn't your thing, this is the route to go. But if programming interests you, or maybe you'd like to change or add a feature, say add more memory, change the key assignments, or use a Bluetooth keyboard and display like the one used here for something totally different, then I think you'll want to download the repository's source code. The good news is this project was developed using Visual Studio Code, Platform IO, and the ESP32 framework. Now many of you may have this tool set already installed. If so, then linking the repository's URL to VS Code may be the easiest method to get your ESP32 flashed. On the other hand, if you need to install these tools, I'll try to give a quick overview of how to go at it. Windows 10 users who are using this version of the ESP32 for the first time will need to download the CP210X USB to serial drivers and install them, because Windows won't find them on its own. To see if you fall into this group, open the Windows Device Manager. With it open, connect your ESP32 to your computer and watch how the Device Manager responds. If it looks like this, then you need to go here, select Downloads, and download the CP210X Universal Driver package. Extract this package to a folder of your choice, then use the Device Manager and its Update Drivers option and its Browse button to navigate to the folder you extracted the driver files to, and Windows will do the rest. When done, you should see something like this. Notice I now have a Device Manager entry, ports COM and LPT, and it shows Silicon Labs 210X has been assigned to COM3. Remember this COM assignment because it's likely not going to be the same as what's shown here. What you get will be needed later to flash your ESP. Also, be aware the number part of this entry can change when you connect to a different USB input on the same computer. Linux users don't need to worry about setting up a driver, but you folks may need to configure the user group permissions in order to see the connection. Okay, now that we have that out of the way, it's time to download and install VS Code. Go here and select the package that matches your system. I selected this. Double-clicking the exe file starts the install process and generates this pop-up. 7 pop-ups later, you should see this. And if you leave the Launch Visual Studio checked when you click Finish, you should eventually see this. Next, what I recommend doing is on the left border, click the third icon down, and if you don't have Git installed in the adjacent panel, you'll see this, Download Git for Windows. Ignore the PIO home screen shown in the center frame of this screenshot. We'll deal with that later. When you click the download button, you will get this. Clicking Open takes you here. Now continuing our Windows 10 install, download the 64-bit Git for Windows. And now in your download folder you should have a Git exe like what's shown here. Like we did with the VS Code exe file, double-click this exe file and pretty soon you'll see this. Stick with the defaults that come with the next umpteen dozen pop-ups. Eventually you'll see this, and finally this. For what we're doing here, there's no need to set or either check boxes before clicking the Finish button. Now restart VS Code and click the third icon down. This time you should see this. When VS Code links to GitHub, it will automatically install the needed packages to work with the repository source code. Click the Clone Repository button and notice in the top center you're now being asked to enter the URL. Enter the project URL as I did here. Now you'll be asked to select the folder where on your computer you want your copy of the project's files to be stored. What its name and where you place it is your choice. In my case, I selected the same folder that all my other Git projects are. After that, you should get this pop-up. Click Open, click Yes to this pop-up, and you should be here. One thing I want to point out is in VS Code, whenever you see the clock icon, like shown here on the third icon down, it means VS Code is busy. Don't try to do anything until the icon disappears. Now, while I don't have the screenshots to show it, while the project is being copied to your computer, VS Code will recognize that it needs the Platform I/O plugin as well as the ESP-IDF framework and the matching ESP dev board, all of which will automatically be downloaded, assuming when you're asked you let it do it. So watch the screen as it goes through the configuration setup process. On my Windows machine, this took well over an hour to complete, so have patience and let it do its thing. More than 1,000 files will be pulled in, and the Platform I/O part will need something like a gigabyte of space to host this material. On my machine, it seemed to really get bogged down looking for virus threats. As far as I could tell, none were found. Now, when it's finished, the clock icons and the traveling blue lines are gone. You have one more thing to change. Click the top left folders file icon to expose the files in this project, and down near the bottom find the platformio.ini file. Open it by clicking this entry, and in the center edit panel find line 15. Uncomment, by that I mean delete the hash symbol, and adjust the upload port entry to match what you determined earlier when installing and verifying the CP210X drivers. When done, save the file, that is, hit Ctrl S. Now you should be ready to compile and flash the project to your ESP32. On my machine, the first time through, this took roughly a half hour to compile. Don't worry about any yellow warning text, but you don't want to see any red entries in the bottom terminal panel during the compile phase. I usually use the upload and monitor option. To see and start this process, on the left, click the Platform I/O icon, the seventh icon down. If all goes well, the flash process should complete with the terminal output looking like this. And then, when the ESP32 program starts, it will move on to look something like this. The next order of business is pairing your keyboard. Basically, at startup, the program gives you about a 10-second window to find new keyboards. That is, a keyboard that's never been paired with a unit. You'll know the discovery period is ended when you see the none found message. So have your new keyboard powered and discoverable during this interval. How you do that varies with the keyboard. On the other hand, keyboards that have been previously paired can be powered up anytime the unit is on, and it should connect and resume processing your keystrokes. Now back to linking a new keyboard. The pairing process can take one of three routes and depends on the keyboard's own pairing protocol. Some you'll need to do nothing, but wait for the status line at the bottom of the display to turn green. Others may require you to enter a predefined pairing code. For those, refer to the instructions that came with your keyboard. If it goes the third route, a pairing code in blue will be presented on the display. All three routes, when successful, will end with the keyboard's hex address at the bottom of the screen displayed in green. This signifies the unit is ready to convert your keystrokes to code or execute any of the special key commands like Control-T for tuning, constant key down. Now that we have the unit up and working, let me point out a feature that wasn't reviewed in the Black Pill video. That is, pressing Control-S takes you to the User Preferences screen. Here you can enter your call sign, the send speed that you want the unit to wake up with, and the canned memory text to be sent when the respective F key is pressed. One thing to understand about this screen is whatever is changed here is what you get when you go back to the main screen. But unless the save key was operated, those changes won't be there at next startup. The tab key or the up and down arrows move you from setting to setting, while the left and right arrows can be used to move the cursor to the character position within the current setting to be edited. Also, all edits on this screen are done in the overstrike mode. And finally, the debug mode is mainly for Bluetooth. When enabled, a more verbose set of text messages will be sent to the USB serial port primarily during the connect process. Now, for those of you who, like myself, are new to RTOS and have applications that depend on precision timing while multiple processes run concurrently, porting this project from a single-core multi-timer architecture having a well-defined priorities to the RTOS environment, for me, proved to be a bit of a challenge. Depending on where you enter Express's documentation on timers, you can go down some rabbit trails that simply go nowhere. Ultimately, I found this video series that helped me get things sorted. So if you're struggling with something similar, check this series out. In my opinion, they're well thought out and to my liking covers a lot of material quickly. Remember, YouTube has a pause button. To explain my dilemma a bit further, the issue was the project has two timers, a display refresh timer that runs at approximately 30 frames a second, and the second timer I call the dot clock, which is the heartbeat or pacemaker of the CW generator. Its interrupt rate varies with the WPM setting. At 30 words per minute, it fires 25 times a second. Now, most of the time, to do the housekeeping assigned to the update refresh process, only a few CPU cycles are needed. But eventually enough keystrokes get processed that an entry will require the text on the display to scroll up a line. The scroll process is not native to the display, and that means the ESP32 has to sequence the commands needed to erase the display and reconstruct the last 14 lines of text, but moved up by a line, all via the serial SPI link connecting the processor to the display. Collectively, this action takes approximately 165 milliseconds to complete. During that time, the dot clock will fire at least 4 times. That is, the time needed to form a dash or 2 dits. So dot clock interrupts must have priority over the refresh process. But some dot clock events create state changes that trigger moving the highlight cursor, the display cursor that indicates which Morse character is currently in play. But if the display is being scrolled, where is that character physically on the screen? The way I dealt with it was to use an RTOS queue. Queues in RTOS are buffers where one process adds data to the top while another process retrieves data from the bottom of the queue. So given that the buffer is big enough, the data in rate can at times be faster than the data out rate. In this project, dot clock events add state codes to the queue, while the screen refresh process, after updating the displayed text, pulls the accumulated cursor states from the queue. This keeps the ear happy with Morse characters being formed at a constant pace, while the eye, being more tolerant to change, perceives the highlight cursor sequencing along the text appropriately. Well, that's it for now.